Olha, só para dizer uma coisa.
Sim.
Não sabes trabalhar com isso?
Não, vou dizer aqui ao laser.
Sim, ao laser, sim.
E aqui é para andar. Ok.
Se tens coisas tão pesadas, pá.
Ok. Isto vai ser no... Ok, está tudo, está.
Podemos começar então?
Sim, estou só aqui fazendo os testes.
Right, so welcome everyone to NIA's seminars, and it's a pleasure to welcome Armando Vieira from Closure to start off the seminars in 2014. The seminar today is a bit different. It's not exactly about physics, but it's might be some interesting techniques that maybe at some point some of us might use. So Armando now works at Closure, which one that you know. He's originally a physicist, now doing different things, and he also taught physics in his F for around 10 years, but that's now in the past. So Armando, it's a big pleasure to have you here. Looking forward for your talk.
Thank you very much. So, as you may have noticed, yesterday a friend of mine called me, Armando, I want to go to your conference, but what is the topic? Is it just for geeks or is it interesting? And I go, no, it's interesting. come on. I like to her, but so I decided to change a little bit the topic to make it more broad range. So I try to keep a balance between academic presentation and also business oriented, because these topics are being utilized a lot in the business, and but I'll try to keep the balance between both sides of the equation without boring too much. So I'll start with a provocation that for most of you I think are physicists, that about the simple and the complex. Here I enumerate some problems that I call simple and some complex problems. I will call it simple problems. Most of the problems that physicists are dealing with now, I will call it as simple problems. I know it's a provocation. They're not. I'm a physicist, I know. What is the radiation of emission of a black body? How do particles interact? How does a system composed of a very large number of particles interact when in equilibrium? Why it is simple problems? Because somehow we can reduce these problems to simple elements, and you can apply reductionist techniques and use some master equation of some kind of very, very simple, very reductionist equation that you can derive all the behavior of the system from these equations. Unfortunately, the world, or fortunately, the world is composed of also another kind of problems that have been a challenge up to now, that are called complex problems. How does economy as evolves, behaves and does evolves, as João Cruz has been dealing with or in this PhD. And, how does a out of equilibrium system behave? How does the brain represent the world? How do we learn? So also this kind of problems that I think they are not only complex but almost impossible, concerning weather prediction. Is it rain in 10 days? Maybe you can predict in 10 days, but in 10 years I think it will be impossible. So this is where the field of neural networks have emerged from the necessity to understand these complex problems and to address and to understand the world in the different perspective. I will start, since you are an academic background and a physicist background, so I will start with a problem. It's the accelerating universe, as it's one of the greatest discoveries in this last century. So it was discovered, this problem was hunted, was found by hunting supernovas that are rare events in the sky. They are hard to find. They use neural networks to find this, to help to find these events in the sky, and this was not possible without the use of neural networks or any kind of machine that can look at very large amounts of data and extract features from this data and help the researcher in this findings. So my topics here are somehow condensed in these 6 points. So I try to give you a little overview about what is machine learning. Essentially, machine learning is finding features, patterns, and representation. Sorry for the spaces. Oops, no, it's okay. I thought the PDF conversion has hit the spaces. No. So I will go through a little bit the connectionist approach. There's several approaches for machine learning. I've been working mostly on the so-called connectionist approach, which where neural networks lies, and I will go a little bit about the applications that I've been working in this 10 years or so. Then I move to deep learning. I will call it revolution because why it's revolution? Because I don't remember from as far as I have been following this field, I don't remember a single architecture of a neural network that have gained so much success in so broad areas. So these architectures have been won successively contests for machine learning with difference from competitors that is outstanding. So I will call it a revolution because not only for this practical success, but also from this architecture. I think it's very interesting, and I will give you a brief overview of that. Also, applications of this technology, I will go a little bit on that because they are interesting. And also, if I have time, I enter into with another provocation concerning what's happened when you mixed these algorithms with big data, the so-called big data reality, where you have so many data at hand, and you can feed this data with algorithms, and the outcomes are, in some cases, outstanding. So, what is an intelligence machine? What is intelligence? Was Deep Blue intelligent? The machine that won the chess contest with Kasparov. What is intelligent? Watson. Was Watson intelligent? Watson, for the ones that are not aware, I don't know if all of you know what Watson, the machine that won the. Okay, Watson. Deep Blue, everybody knows, I think. Watson was a machine developed by IBM that won a contest called Jeopardy, or in Portuguese, Quem Quer Ser Milionário. It's a very hard. It's different from Deep Blue. Deep Blue, the chess, is a closed problem. You know the rules. You know, can calculate all the probabilities of movement of the pieces in the table. So it's very close problem. It's very somehow structured problem. The Jeopardy problem is open questions, like who was the queen of France when some event occurred, or so these kind of problems. They are open problems. They can ask in the school. A student or a teacher can ask students in the school. And Watson beat all the humans in this contest. So the technology they use is a kind of a mixture between some of the algorithms they use is, I will speak about that here. They are neural networks. Some of them are deep learning networks. Other are just munching large amounts of data, going to Wikipedia and crunching all these documents and try to find patterns. But it's not easy. I mean, information is there, but it's not always evident how to extract that. So Watson won this contest. This is Watson is intelligent. Is it Watson intelligent? Or Google? Or have you ever made a machine that achieved the level of intelligence of a rat? Well, I cannot answer this question because intelligence is, I call it as beauty. You notice beauty when you're in front of someone that is beautiful, but you cannot describe what is beauty. Intelligence is almost the same. So for me, I call intelligence something that is able to surprise me. Okay, when I get the result, where I get some answer that is not what I'm expecting, I would call that coming from an intelligence device. There are other definitions like Turing, but for me it's good enough. So this is a brief history of connectionism. I call it 3 steps.
It's not very good.
I know it's not very good, but it's my definition. You can have your own. You should free to have it. the web concept of connectivity concept, the multi-layer perceptron and the deep architecture. You can create another ladder of evolution from the connectivity. I create this one. Web concept is the most fundamental one. It's essentially one of the ways the brain learns from the environment by connecting to neurons or to regions of the brain by stimulus and response. So like a Pavlov stimulus. If you see the ring of the bell and you see the food, the dog learns how to connect the sound, the bell with the food that he receives as a reward. So this is a Webbian mechanism, and it is very well established that the brain learns by reinforcing connections between neurons. The multi-layer perceptron tries to incorporate this behavior, and I will talk about that a little bit later. So, a brief history of connectionism. In 1943, the Black-Pitts created the first perceptron. It was a very simple perceptron, tried to stimulate two layers of neurons that are connected, the input layer and the output layer. And the way these layers are connected, they are trained by adjusting the weights between the inputs and outputs. So this is essentially a very simple learning machine. In 1968, I think around this year, 68 or 69, Mies came up with an argument that puts out all the research on this kind of perceptrons. He came out with a set of arguments claiming that these perceptrons are not good enough to do complex computation. Okay, so he came out with a series of reasons for that. Some of them are still valid today, but most are not valid because we have evolved to another architecture. It's called the Rumenhout perceptron. That is different from the perceptron from Black-Pitts. It's the perceptron that has not only two layers, but more layers in the middle. And by using this clever architecture, we have been able to circumvent this argument and create really useful machines. And in 2006, Ethan published a paper on the Nature, I think in Nature of Science, where he came up with deep learning networks to create an even bigger and more complex networks. As we all know that we have been mostly exposed not to these kind of machines, the connecting machines, but to symbolic machines. Symbolic machines are Turing kind of machines. They process symbols one at a time using a very high-speed processor, okay? But they are serial machines, okay? They take a symbol at a time. They don't know what kind of symbol they are processing, if it is a number, a letter, or image. They process it at very high speeds, following rules inscripted in the program, and they have been doing a quite good job up to now. Problem is that these machines, although they are very, very good, they are not as close as to our brain in lots of tasks, like image recognition, like voice recognition, like learning, like abstractions. So we have some difficulties living with this kind of two worlds apart. The way the brain processes information is completely different. For instance, it is well known that when you process image in the retina, you don't do a pixel at a time. You do the whole bunch simultaneously, okay? And you process and feed-forward this information through different layers of processing unities in the retina. So it's a completely different approach from the I'll call it tyranny of the CPU that controls all the operations. And if a single neuron or a set of neurons collapse, there is no problem. The system works and can repair itself very fast. In the programming language, if you miss a comma or a single digit, you can collapse all the program. So it is the parallelism is a way for the brain to compensate from velocity. So since the brain is not as fast as a computer, it compensates this fact by processing data in parallel instead of separate. So this is a very simple schematic representation of a neuron. It has a set of synapses, connections between this neuron and other neurons, okay, and called the axon. This connection that comes out of the neurons and then ramifies to other neurons. You can have as much as 10,000 connections between one neuron and the next neuron. So it's a very densely connected mesh. And you can have up to 10 to the 11, I think, neurons in the brain. So it's a very, 100 billion neurons in the brain. So it's a very large number. So the human brain is a very densely connected machine. And the way the brain learns and do all these tricks that we know, it's by adjusting these weights. Okay, weight adjusting is the essential mechanism for brain to learn and explore the world. This is a virtual cortex, as I told before. It's well known that the processing is done by layers. Okay, each layer processes and extracts features from the image at a different level, at a different organization. So this is the trick the brain uses to recognize objects in video. And here is a very simple artificial neuron. This neuron has the element of the neuron has a set of connections, of inputs, okay, that is fed to the neuron. Each input has a weight that is kind of a regulator for the signal that each variable is fed in the neuron. And then, essentially, a neuron is an integrator. So it sums up all signals, and it passes the signal through a transfer function, in this case, a Heaviside function, but it can be a sigmoid or hyperbolic tangent, whatever you may find useful. But it's very important that this transfer function is non-linear. Okay? If it is linear, you don't get interesting stuff. It's very important to have a non-linear transfer function in order to be able to learn complex functions. Okay? And then we have the output. Okay? And so this is essentially an artificial neuron that we will use to create our neural networks. This is in this case is represented a simple multi-layer perceptron. This is a building block of research in the 90s, in the 80s. It has performed very good in lots of tasks. And essentially, this is a regression machine. Okay, it's a mapping machine that maps inputs to outputs. Okay, through a nonlinear transformation. Okay, we have here the input nodes. Can be oops. What's happened, John? Is that it? So the multi-layer perceptron has the input layers where we receive information. It can be pixels from an image. It can be signal from a spectra. It can be voice. It can be whatever you have to classify. And then you have something here in the middle that will help to transfer this information to this hidden layer, and then you have something in the end where is your output lies. In this case, it can be, for instance, you are trying to classify. It can try to distinguish between cats and dogs. It is an actual problem that is being solved by lots of guys in the competition to know the ones that can separate image from dogs and cats. It's not as easy as it looks. I will talk about that later. So this is the categories you have in your output. And how do you train this machine? Well, it's easy. Yes, as long as you have enough examples, evidence from your problem, you just give them the inputs that you have, in this case a pixel from the image, let's call it, and you train the machine by, this is called a supervised training, by giving the outputs that corresponds to each input. Okay, so this is an image of a dog, this is an image of a cat. Okay, and you feed the machine with different with different examples. And the way these weights are adjusted is by a mechanism, algorithm called the backpropagation algorithm that is essentially a stochastic gradient descendant algorithm. Okay, so essentially tries to figure out what are the directions where you should move the weights in order to reduce this difference, this error that is the difference between the target and the output of the network. Okay, so you start by randomly initializing the weights, and then you calculate this error, and then you create the gradient of this expression, and you calculate this correction of the last layer. Okay, propagate this to the last layer, and then you go forward to another layer. I will.
Sorry, what is T?
T is a target. So why it's the output you have. T is the target. It is something that you are expecting. So, for instance, if this is a classification problem, you have to here if for cats, let's call it cats and dogs. So if the image is a cat, here it comes 1, here 0. If it is for a dog, here it comes 1, here 0, and so on. So each node goes to a single category.
And that's for learning, just to adjust the weight.
Yes. That's the trick they use. Yeah.
And another, the gradient is with respect to what? Is neighboring nodes?
I'm sorry.
The gradient.
Yes. The gradient is with respect to the weights. Okay. You minimize. You derive this to respect to the weights. So you get a correction to the weights. You try to find a new weight that will put these expressions lower, this value lower. Okay. So I'm not going into much details. We have this. There are some tricks in these algorithms. Some of the algorithms have a lot of tricks. Okay, I've not tried to oversimplify this. Some algorithms, in fact, have a lot of tricks. This is kind of a black, not magic, but black heart. You have to really understand your problem. Each problem has different difficulties, and is something that is dirty about these machines is that you have to know your problem, and this fine-tuning of parameters and the learning rates. There's a lot of details that each problem is unique, and you have to really understand and get the feeling of the problem. It's not easy. I mean, it's something that you have to have some experience to work with. So the pseudocode for the backpropagation algorithm is essentially here. So you start by putting the inputs. This is you calculate the difference between the expected value and the result you have. This is for a problem of interest rates. It's different for all case, but essentially you try to derive the expression for correcting the weights in order to reduce the error. So in this case, we have here a function that we try to make a smooth fitting to this point. Okay, this set of points. Okay, and you try to guess what function are this point extracted from. This is the real function. Okay, to settle points. And here is the reconstruction that the neural network have done based on these dozens of points. Okay, so it's not bad. And here is the error. So the message here is that as long as you have enough training data, essentially the network, what it does, it fits to this data. Okay, and it can be arbitrary complex fitting as long as you have the data. So the information is on the data, not on the machine. The machine is relatively simple. How the training is performance, and how much data you have to feed the machine is there. That is in information. Okay, because the machine in itself is relatively easy. And so I'll come back to this kind of learning problems a little bit on the specific cases later on. So essentially, you have two kinds of problems: supervised and supervised problems. Unfortunately, these devices or this architecture is only good for supervising problems. You have to have labels. You have to have examples. You have to know that this image is a dog and this is a cat. It's not the way I know. It's not the way the brain does the job. Somehow the little child can understand very easily which animal it is by just looking at some examples and can extrapolate very fast, identify. Sometimes they do mistakes, but they learn very fast from few examples. It's not the way these devices work. You have to have, in this case of image, you have to have hundreds or tens of thousands or tens of thousands of examples to train properly the network. Okay, so it's not very efficient. And for the supervised problems, these problems that we have no labels, no data, no information about this, only have data. We have to somehow extract features from the data. These machines are not very useful. They are not very good at finding the terms and the supervised learning. The problem somehow is to help these devices. We have somehow to create a representation of your problem in a proper way. So let's consider, for instance, that you try to understand or identify a bicycle by looking at some image. If you try to feed this bicycle, this image of the motorcycle, to a neural network, we have a low success. Why? Because what the neural network sees is only pixels. It cannot see shapes. For instance, the neural network is not capable to see that this is a wheel, okay? And the way the wheels are organized at some distance, they have some colors in it, so it's not able to see. The neural network sees each pixel separately. So what was the research in the last 10 years or 20 years mostly being focused is extract features that see where is a wheel in the image. What is the aspect ratio of the image? How is the color histogram of the image? Okay, so extract these features from the image. Some kind can be tricky. This feature not evident. And instead of feeding the image to the network, you feed the feature that you extract from the image. Okay, it calls feature extraction, and it's done by hand. The network is not capable. It can do some simple feature extraction, but it's not capable of higher level feature extraction, as the brain is able to do. So I will show you by the end of the talk that we have now ways to circumvent these difficulties and can extract automatically features from the data. But these networks cannot do it. So, however, they can do some nice problem solving that a child can do. In this problem, for instance, is a typical problem for a child. Let's say, if you go along the street, you see some kind of high-level classification of objects. Let's say, this is a living thing. He's a plant. If it is an animal, go here. And then it's if it is a tree, it has bark, it's big. It can be a pine, and it's green. If it is a oak, it's tall. I don't know what is written here. So you somehow create in your brain. Every one of us has somehow created in our brain a mapping. It's an implicit mapping of objects that we see. So you know what attributes the object has. You know how they are organized. You know that fish have a separate category from birds, and birds from flowers. And somehow these two, call it kingdom, the animal and plants, have very distinct characteristics. Okay, is a network capable to understand and somehow map this information? Yes, it can. I call it mapping, not memorizing. Okay, it's very important. This is not a lookup table. It's not memorizing, as in some schools. It's the method of memorizing things. It's not memorizing, just it's able to generalize. Okay, so if you fed this kind of a multi-layer perception, with these objects like pine, oak, rose, daisy, robin, canary. Okay, it's this item, and each time you have an item, you activate an input, and this is the relation. Okay, if you have another line for the relation that you create between these attributes. Okay, and you give some examples to train the system, like say, okay, a pine, in this case is a canary, okay, can grow, can fly, can swim, okay. So give some attributes for each example, okay. And after some examples, the network is able to somehow learn the structure of these objects, okay, of these animals. So the only thing you have to do is to run it through several epochs. Called epoch. It's a full iteration to your data set. Let's call our data set is 20 examples. So you give the same 20 examples again and again to the network, not once but 500 times. So this is 500 epochs. So and you continue to teach the system. It can take 1,000 epochs. It can take 1,000,000. Depends on the complexity of the problem. It depends on the learning rate. It depends on some parameters. But the important thing is that it can learn the structure. These three relations can be learned. And if you do a thing called the PCA, that PCA it's principal component analysis, essentially to decompose the problem into two big components. You see that the machine is somehow created a mapping, a very good mapping of the kingdoms, animal and plants, and in each kingdom you can create different subclasses like a bird, canary, and robin. It's birds. This is for fish. This is for plants. And this is for trees. So somehow you can learn it has capabilities to learn very similar to what a child can do with some examples. Okay. However, there are some difficulties in training these devices I showed you before. One of the problems is the curse of dimensionality. It's a very important problem when you are dealing with big data, the buzzword of the moment. So, in the present problem, we have just a few categories. Now, suppose you have a data set like the problem we have dealing with Closer recently. They have 600 inputs. Okay, if each input, let's call it, each input has 10 categories, 10 possible labels. So you have a very huge domain space where the network have to look for a mapping. Okay, so this is simplified in this case. We have two dimensions. Okay, let's call it x1 and this case is x7 and x6, and you have three categories. Okay, you have the blue, the red, and the green. And if you have a point here, the problem is which category does this point belongs? It's a blue, a red, or a green. So the way you can do it in the simplest way is just counting for each square, counting the number of colors that lies in this square. In this case, the majority of labels here are red, so this square is red, and this point is classified as red. The problem is if you have a huge dimension, most of these squares are empty. You don't have points lying in here, so you don't know how to properly classify these new points. Okay. There are other problems in learning with these machines. It's the problem of overfitting. Suppose you are trying to fit a very simple problem. You have these blue crosses. This is your experimental data with some errors in it, maybe, and you try to map a function that learns this data. Okay. If you do it with a very simple network with only one hidden neuron, a hidden layer and a hidden neuron, m equals to 1, the most you can expect is something like this. It's a kind of a reverse sigmoid function. Okay, if you have a more complex machine with 3 hidden nodes, you can learn a more complex function. Okay, But if you continue up to m equals 10, in this case, what we may learn is a much more complex function, but if this data has some errors in it, you are learning the errors along with the data. So we are trapping in a problem called overfitting. Okay? So you have somehow to control the complexity of your model. You cannot create a model that is more complex than the data. Somehow the complexity of the model has to divide the complexity of the data. Okay? If you plot here the way we control this is by using, there are several ways, but one of the most used is by using two data sets. The learning data set and the testing data set. So the learning data set is some data that you feed to the system again and again in order to reduce the error. And the test set is some extra data that you don't give during training to the algorithm. You just present to the algorithm after the training was done in each epoch, was performed, and you evaluate the performance of the algorithm on unseen data. Okay, and you will see that there is some point where we have a minimum. That's called this point here. So here is a point where the generalization capabilities of the network is better. If you continue to continues to train the system or give more complexity to the model, you will end up with higher testing errors. Okay, and this is not a good thing to do. This is more evident in this case of classification. Here is, suppose you have try to separate where are the blue, the greens, and the reds, and you see that this case on the left is very good in learning. You can learn all the details in your data. The problem is, okay, suppose you have a point here, okay, in this region here, or a point here. How should we classify this point in here, or a point around here? How should we classify this? If you're using this model from the left, you end up with large errors because you are learning too much. I mean, there are maybe errors in these data sets. It may be that you miscollect the data or something happened. And if you're learning this complex mapping, when you try to apply it to unseen data, the probability that you have large errors is high. Here you have a training error of 10%, a test error 25, almost 26%. And in this case, we have a training error that is higher than in this case. It's only 60%, but the test set error is only 22%. So this model, although simpler, is better for generalization. Okay. So these neural networks are very tricky to optimize. It's very easy to end up with local minimum. It's non-convex problems. There are permutant invariants, so it means that you don't have a unique solution. You can have several solutions. Okay. Oh, the time is running. So I have to go faster. So this is an optimistic view of what is the learning in the neural network. In fact, things are much more complex than this. So you have to take careful not to end up in local minimum. The way to do this is by putting some momentum, some stochastic seed in the algorithm in order to not be trapped in local minimum. Okay. So there's a lot of difficulties. I will not go in that. I leave to you. So let's go to the applications. There's a bunch of them I've been working. I will start by ion beam analysis. Problem that I worked with Nuno Barradas for about three years. The problem it's a Rutherford backscattering where I'm sure you know what it is, Rutherford backscattering, and so it's I will not go into the details. And the problem is in Rutherford backscattering you have this spectra, okay, and you try to analyze these, extracting some information. In this case, information you want to extract is what are the density of the implantation. They have germanium implanted in silicon, I think, in this case. What is that? Germanium implanted in silicon. What is the depth of the implantation and the concentration of the implantation? And this information can be strained by analyzing these peaks. Okay. This gives information about the density, and this information, the distance between this peak and this one. This surface gives information about the depth. This is a very complex problem. It normally takes a PhD several hours or a day to analyze a single spectrum. Okay, it takes a lot. It's a lot of time-consuming problem, and it's not even easy because there is a lot of particularities. Like if you analyze your sample with different angles, you get very different spectra that comes out from the same result, the same material. So use, I will call it deep networks, not deep, really deep, but these different networks that are already big enough. So we have, in this case, the input layer is about 130 inputs that corresponds to the energy to each channel. You have 100 hidden neurons in the first layer, 80 in the second layer, 50 in the third layer, and then the output. And this is the best architecture for minimizing the test set error. It's 4.1. It's quite good. Okay. This is a comparison between the prediction and the results, and the experimental results is quite good. We have been lucky in this we were able to generate artificial spectra. So you can have a machine to generate spectra. You can have as much as you can. So in this case, we have, for the first time, we are being able to make real-time diffusion, analyze real-time diffusion with Rutherford spectra. This is platinum implanted. Not remember. It's a thin film, nickel. Platinum and nickel, I think. It's a diffusion problem. So they insert some platinum in analyzing real time the diffusion of the it anneals it was suffer an annealing, and here you see in real time the way the atoms move inside the sample. Okay.
So what does it looks for peaks to identify which energies?
I'm sorry?
It looks at the spectrum for peaks.
Yeah.
Identifies the energies and compares with some database that is
no, it's simply analyze. I mean, this problem is the difficulty they had before in analyzing real time is that it took a lot of time to be done by hand, okay, or even by their own algorithm. So the difference is that they have been able to instantaneously know what are the concentrations, the depths of each of the elements inside the sample. So
is it because it does it faster?
Yeah, because after you train the network, you can learn that it's a very complex mapping. That network, for instance, it took. So if you,
Yeah,
so it's about
look for peaks and
yeah.
energies.
So okay. I have to speed because your computer stuck wrong. Okay, I'll go. I also work with the telecom problem for churn detection. We did this. The problem here is to find the fixture by analyzing the CDR record from customers, see which calling who is calling who, and trying to extract features from the churners. When the churner leaves, it somehow propagates its influence to the neighbors, and when you feed that to the network, you can also get interesting results. I'm not going into details. Also, AdWords optimization. This is something that we have been working right now. It's a very complex problem also, and also very interesting. I don't have time to go into that, unfortunately. I also cannot disclose some of the information. It's quite recent. Also, a problem that we have been working a lot is bankruptcy prediction and credit scoring. It's a classification problem. The problem is that this problem has only a small particularity that we have in your data companies. Okay, they are, some of them are bankrupt or went bankrupt, and other ones are not bankrupt. And you want to score this company. Okay, you have to give a value, what is the probability for this company to get bankrupt. But in reality, you don't know, because you only know the event of bankruptcy. You don't know the extreme event. You don't know the event in the middle. You somehow have to guess what is happening in the middle. Okay, but you don't have information to train the system. You only have the occurrence of extreme event. Okay, it's like trying to find when someone will die, or get the probability that he will die by knowing only when he dies. Okay. You cannot do this. It's very hard unless you have some other insight or some other features to feed the system. Okay. Somehow we deal with this problem with a semi-supervised approach. I will not go into details here. Sorry, I have no time. Also, hotel demand using Google, very interesting problem. This kind is a time prediction problem. It's something you, instead of trying to simply classify, we just use historical data, like what are the hotel occupation in certain periods, and compare that with the keyword that the users are searching in Google, let's say 3 months before or 6 months before, okay? And by analyzing this flux of information, we can extract patterns and can help the hotel to say, okay, my demand prediction for a certain month will be higher or lower than it was a year before. Okay, so you can somehow adjust the prices based on this flux of information. This is a recent problem, also very interesting problem from a credit card company. This is what they have implemented right now on the left side. I've been working with Inês and João and Vieira. And from the right side, we have somehow what we can do up to applying, not in this case, not neural network, it was random forest. Neural networks have some difficulties in this case of problems, but we somehow have been able to increment a lot, try to separate these two classes of customers. They are most of them are already bad customers. The customers are subprime customers. Any bank does not give credit to these guys, so they already some bad track record on the credit history. But the problem is to let's separate the really bad ones from the not so bad ones, and somehow I've managed to do that. Of course, there is this gray area where there is some superposition of these two categories. The guys that are okay, that they will apply to their credit, and the ones that don't pay. But it's much better than it was before. Just to give you a glimpse of this problem, this is a plot. In this case, we have about 600 different variables. It's a very call it a big data problem. 600 different variables, and if you plot by the importance of each variable as in the graph, this is for the first 100 variables. You index the importance of them and just plot the graphic. You see that it's almost flat. So you don't have a single variable that is determining what is the customer will pay or not pay. It's a full range of information. It's fully distributed for all these variables. Okay, and you have to be clever not to throw away the water with the baby. So you have to take all this into account. So neural networks are very good. They are not silver bullets. They have some tricks that we have to deal with. And okay, I will go. So where is the intelligence in these machines? Of course, there is no intelligence. We may call it they are stupid machines. They are just regression machines. Okay, I agree with you. Okay, but isn't that the brain also stupid? Aren't the brain just a regression machine, just a classified machine? Of course not. It's more than that. But at some level, some brains. At some levels, we may treat the brain as a pattern recognition machine. Okay, but essentially the information is in the weights. Okay, as long as we have enough training data to feed the system somehow can perform very clever tricks. So we still need talking about the training and comparing to the real brain. So I will go. I cannot miss this part because it's 5 minutes. Just briefly. Okay, 10. Let's put it 10. Deep learning approach is quite new. It's something that I came out this very recently, so I'm not an expert in deep learning. The information I can present you is something that I read and I test with me in some cases, not something that I really put my hands on. So, the idea is very interesting. So, from the 80s, it was proposed a machine called the restricted Boltzmann machine. The restricted Boltzmann machine is something very appealing to the physicists. Only by the name, Boltzmann is quite good to have Boltzmann in the name. And the idea is different from the machines that we've been dealing up to now. These are not feed-forward machines. The previous machines, you put information here, and you get output there. This case is different. They are not. They go both ways. Okay. So somehow they try to find the weights in this hidden layer. Okay. Suppose this is an image. They are applied a lot to image processing. So suppose you have an image, and you try somehow to find patterns in the image. So try to model the image with prototypes. Okay. In quantum physics, let's say we try to find the wave, the eigen functions that compose the system. Okay. And you have to train these weights to determine these weights by an algorithm that in the end what we have is a representation of your inputs coded in this hidden layer. Okay, and this has to be stable. We have to run the algorithm to a point where it is stable. But this was very tricky to do, because this problem is much harder than the previous, because it's a recurrent machine, okay, and it most of the cases it goes to a divergent state, okay. You cannot converge, okay. It's very difficult to make it converge. However, it has nice properties, like the fact that it is an associate machine. Okay, you can do associative memory with these kind of machines. Like you put the tail of the cat, and only by the tail of the cat, the machine can somehow evolve to a Bayesian of attraction that represents the image of a cat. Okay, only by the tail. So they are very, very nice features. Unfortunately, no one's know how to train them properly. Up to I think 2002, Eaton comes out with an algorithm called contrasting divergent algorithm. That is, I will go a little forward to explain a little bit. Skip all these formulas. I don't think you are. Okay, too much. Think too much. Just to give you a glimpse, the trick they okay. Okay. So we're trying to do a Gibbs sampling of the states of the hidden layer. Okay. So as I told you before, this is, you give the data, you somehow try to compare, make a estimation of the free energy between the states of the data and the state of the hidden machine. Okay, you make somehow a projection between the two, and use these training weights to make a reconstruction of the initial data. Okay, get a reconstruction. Okay, then you go again in the second iteration. You try to create a new learn a new set of weights and try to build another representation. Okay, so on and so forth. And that what you have in the end, in most cases, it's something completely different from what you are supposed to represent. It's just fantasy. It does not converge. And what it does, it's a very simple trick. It says, okay, I don't care if we converge or not converge, I will stop it here. You put here a cutting point, okay, and it gives two different data sets called, to make it contrastive. You make a real example, okay, this is the image of a cat, okay, this is a cat, and down it gives some noisy image, this is not a cat, okay, and it trains the machine with this, it obliges somehow the machines to learn the representation that it has in the data. Okay, and by applying these tricks and other small details, but essentially this is trick, you are able to train to adjust the weights in order the machine to converge and to represent the input data. And the results are quite astonishing. I think they are amazing. I will show you only a few tricks that this kind of machines can do. So this is the problem of image classification. We have 4 million of unlabeled image, okay, and the problem here is to learn fixtures from the image. As you may know, it's not easy to find the fixtures from the image. What are the edges? What are the shapes? Are they invariant to translation, to rotation? Different light exposures. It's a very hard problem. And they don't care about that. They just feed the machine with 4 million of available image, and it comes out with a set of 10,000 learning features. This feature, each rectangle here is a hidden node from the hidden layer. Okay, so we somehow are able to decompose image into very simple and very interesting features. Okay, and by composing these features, they add up an extra layer on top of this hidden layer. They put an extra layer, and they are able to learn and classify the image based on these features. Okay, so it's a feature extraction. Yeah, dimensional reduction. Yes, and the results are very, very good. They apply this for image and also for text. They classify text, and you see, in image it's difficult to see what feature they are learning or how one relates to the other. But here it's on the data set of almost 1 million documents from Reuters. They are able to recognize patterns like Russian, Rush, Moscow, Yeltsin, Soviet, Clinton, House, President, Bill, Congress. So they learn from the data. They learn features. Okay, that makes sense. Here, for instance, it's the same problem for also image reconnection, and from this set of features, they are able to reconstruct image. So somehow they mimic the capability of the brain to modernize faces, human faces, with features, abstract features. This is amazing. So they are able to reconstruct for a very short subset of numbers to reconstruct human brains. And the way they do this is, I think it's amazing. So this is the feature, the high level feature of level 1. This is a more higher level feature, and then they are able to reconstruct the reality from this set of features. I will go you to an example. So this, for instance, this is a case. I almost finished. Okay, just a very nice demo in the end. For instance, in this case, they are able to disentangle. Let's say you learn image with a guy, okay, and then you put a guy with glasses. Okay, what is this guy? Do I know? If you give it to a normal machine, it cannot understand because you put glasses and it's completely different. Or if you put a burqa kind of shit with a girl, you cannot recognize the girl. But the machine, since it learns features, it can decompose the image between these two elements, the glass and the guy without glass, and put together, it combine them and reproduce the initial guy. Okay, and the same for the girl. This is the same result with other algorithms, so it's much worse. So these are learning features in a much higher level than previous algorithms. This is for text also. This is also done with latent semantic analysis, considered one of the top dimensional projection algorithms for text analysis. And you see how it compares with deep learning machines. So it's completely it's much better results here when you decompose the same corpus of. This is the different corpus of data. No, this is the same one from Reuters, 800,000 documents, and you see that they come out very nicely to different subjects. This is legal, judicial, disaster accidents, European community, interbank markets, energy markets. So somehow, in an unsupervised way, it can learn features from unstructured data. Okay, and this is quite amazing. So somehow it's like you make them rolling of your feature data to a simpler one. Like if you have data spread it out to this complex manifold, you can the algorithm somehow learns how to unfold the data and to project it by putting similar data points to similar regions on the data space, in lower data space. I'll skip this, but I cannot miss one demonstration. Okay. Okay, so I go to a web browser. João, can you help me here? Okay. Okay. This plus that. I will go this plus that. You can if you go to deeplearning.net, you can find tutorials and papers and software. There are software in MATLAB and in Python. The Tiano libraries. It's very good for testing. I will advise you that these machines, these plus that, these machines, I run some tests with my own. These machines are very, they are very. This plus that is test. They are very subtle. They are even harder to train than the previous one. The previous one I mentioned, we have about, in my case, the biggest machine I've ever worked before was about 25,000 weights to learn. In this case, it can be up to 20 billion weights. It's a very, very large machines. It's a lot of local minimums. They are very complex to train. So this is the way they use all these weights to somehow create very high level representation of the world. But they are very subtle. It's very easy to end up with nothing. So the learning rate, the way you initialize the weights, everything is very case dependent and very subtle. They are not. I will not give you impression. This is not. They are not easy to, and they are also very time consuming. It can take days to turn. In one of the cases I trained, it took me all night, and I have to keep it because I tried with a smaller data set. But they have a lot of subtleties. Okay.
So there's no general rule.
No. Even learning algorithms I talk about contrastive divergent, but there are lots of them around there. It's you have to go through. It's a very, very active area. Google has created their own lab. Facebook also created their own lab because they think that these devices are something that's very useful for them. So they contract the guy that invented this, the Ethan. They are working in the Google labs right now. If you search for Google on the YouTube, the Google Talks Ethan, you find two very nice talks that he gives and explains this application. He's the father of this, so he knows much better than me. They are very instructive. But I only saw this application. This case was inspired by text classification. And instead of looking at words as atomistic elements, called the bag of words case, like you create a document and you separate the document apart from the stopping words. You create it as a bunch of words. So normal machines look at documents as a bunch of words. Google most of the time look at documents as a bunch of words. It doesn't know what the meaning. If you are looking at a bank or a river bank, it doesn't know. You just put bank and river or accounting, so it mixed together. In this case, this simple front end is reading a pre-trained network over all entries of Wikipedia in English only, and also Internet Movie Database. So, and it does not only look at the information, the text they are in each document, but it somehow creates a mapping of characteristics of each document. So it condenses 1,000 million word document into a fixed vector of fixtures. Okay, what are these fixtures? they are embedded in the network, but it somehow can represent these pictures. Let's try, for instance, a movie, The Matrix. I draw this one. And let's suppose I want to know what is this movie, Matrix, is related to other movies, but a movie that is less forceful and more dumb. Okay? And the results, it came out with is Blade 2. I never saw it, but it seems dumb enough. And I, Robot. And I Left Ordinary Life. Okay. And for instance, Harry Truman, American, minus American plus Russian. What do you expect to come out? What do you expect? Harry Truman, less American, more Russian.
Stalin, maybe?
What?
Maybe Stalin?
Stalin, yeah. It's a good hit. It comes out with these guys are more information than Vladimir Putin and Boris Yeltsin. Okay, let's put José Sócrates and see what he comes out. José Sócrates. It's very nice. So, if you, for instance, if you put king, less man plus woman, it comes out with queen. It's obvious, but this is not. Let's call José Sócrates. Not Socrates, the philosopher. It's a humiliation for the philosopher. So, okay, no, it's not Socrates. Okay. Let's see what similarities he has. So, George Sampaio is not bad, and Manuel Rambarros. Okay, let's call Socrates, but more intelligent. Let's see if he came out with no. Okay, Paul Porter, the same guy with Paul Porter. Okay, you can play around. It's very nice. It's only English. For instance, Mitt Romney, less experience, more celebrity. Okay, let's try this up. So it came out Sarah Palin and John Kerry. Okay, I don't know why it comes out, but it's so you get the idea. So for instance, Justin Bieber, less man, more woman. So you get this. I don't know this guy, this girl, Christina Aguilera, maybe. So the idea is that for the first time, these machines are really understanding meaning. Okay, not only an image, but also on text. Okay, they somehow map our concepts related together. Okay, they understand the concepts, the text is explaining. Okay, again, there's a lot of subtleties in this. The algorithm, everything in this case is open source. You can download the algorithm from Google. They can use the API. This platform was built on the API of Google. They are quite nice on this. So you can if you go here in the information of this guy that he done this in, I think it was in the 6 month or 3 months period. He does this, so it's very nice. You can go with the blog of the guy. He explains everything there. And this is based on top of this Google API, and you can understand all the details. And it's well. To conclude, I say that we are entering in really, really fascinating times, because for the first time we are being able to digest all these big data. We have this big data available. We have algorithms and the capabilities to process, the power to process all this data, and for the first time we can really getting a little bit closer to the brain, I think. This time, the surprise, the definition of surprise I told in the beginning, is a bigger surprise than anything. For instance, just to finish, recent paper also from a guy on the Stanford came out with an algorithm for understanding, separating and identify dogs and cats in videos. Okay. Automatically, no supervision. Just feed hours and hours of YouTube videos and pictures, and somehow you are able to classify and what is a cat and not or not in the video. And the results, I will tell you, are in some cases are closer to humans, and in some cases better than humans. Okay. Another case, for instance, in the airport, like identifying when the guy picks up the phone and makes a call or receives receives a call, okay, this movement in the unsupervised environment, okay, airport, lots of confusion, lots of guys moving around, no controlled lights, nothing. In this case, we were able to identify about 70% of accuracy when this bunch of guys in the line for the boarding when they pick the phone or not pick the phone. It's better than human eyes. So the human eye cannot do this at the same accuracy. So also robots that can identify long-range and short-range image and can navigate in mazes, very complex. You see, if you go to the web page, you see lots of demonstrations. You see for yourself. It's amazing. They're really getting closer to human capabilities. They cannot think, they cannot abstract for now, but I think we are on the wave of a kind of revolution on this. So thank you very much for your time.
We'll have time for a few more questions before going for lunch. Is there any question? Anyone? Yes, please.
In those neural networks, you assume that every cell is connected to each other, or do you assume any particular?
What kind of networks? Is this deep learning architecture?
Yeah, or the other. Or the
yeah, no. They are stratified by layers. So they are stratified by layers, where each layer, it's built on top of the other. So,
but each cell
in itself, they don't connect. Okay, they don't connect laterally. They don't connect at levels. Okay. Yes.
But each cell from a certain stage connects to the
yes.
other cells of the
the other state. Yes.
And so, when do you introduce stochasticity in order to avoid those local?
You can do it several ways. You can do by adding a momentum, like a random movements. Okay, instead of going as instead of reading the gradient descendant, the term, you perturbate this term with some random variable. Okay, or in some cases, I also forget to tell something very fascinating. Also, the guys make a test where they randomly they disconnect half of these billions of connections and just randomly shoot it off. And it turns out that the prediction are better than instead of having this connection on. So somehow it appeals to the sparsity. Somehow it's something that is well known from the brain. The brain uses a lot the sparsity mechanism to. It's kind of telling the system, okay, don't look at details. Just look at high-level features. Forget about details. If in case of a human face, forget if the ear is more round or more. Or the color, forget about that. Just look at really important features, what characterize a human face. And so, this is also a way to introduce noise,
What about making connections from one layer to another layer?
Yeah, that's what they did. They stuck, and so the image. They stuck layer on top of the other. This is also a very hard problem. They didn't know how to do it before, because we have a problem called the vanish gradient. So as long as you put more layers, you forget information about the gradient because you are propagating information from more layers. And there are tricks to deal with that. So this is not only contrastive divergence, also other kind of tricks. I don't have time, but you can read most of the papers are on archives, so they are freely available. I will advise you that it's not something easy to because there is a lot of details. In each case, each architecture has its own subtleties. Yes.
Any more questions? If not, let's thank Armando again and go for lunch.
Ok.
Pois,
está bem, não estou. Não, eu perdi muito tempo, pá. Isto é muito interessante. Mas vocês, se quiserem lá na net, tem lá muita informação sobre isto. Há aqui um vídeo muito engraçado. Queres ver? Até agora vou mostrar aqui um vídeo. Que é. Tipo, isto vai ao Google diretamente? João. Vai ao Google diretamente. Isto vai, não, se eu puser aqui ele vai diretamente ao Google. Espera aí, não, eu sei de cor. Ok. Por exemplo, eles aqui aprenderam. Por exemplo, generate walks. Ok. Ok. Eles aqui aprenderam fixtures de uma pessoa correta. Por exemplo, fazer análise de vídeo, eles conseguem reproduzir como é que é um padrão de uma pessoa correta ou de uma pessoa a andar.
Fazem faróis. Quando substituem na prática, se eu metesse as luzes nos cotovelos e nos joelhos, não é? Como fazem os gajos dos filmes.
Sim. Veem como é que esses pontos se interconectam.
As fazem automaticamente. Tem tantas vezes que conseguem descobrir quais são os faróis do corpo em vez de espetar nos faróis no corpo.
Sim, pois o gajo.
Por exemplo, este aqui gera caras, por exemplo. A partir da... Isto aqui são as redes da... Isto aqui são os padrões. Lá em cima são os padrões que estão codificados nas camadas superiores. E a partir daqui ele consegue gerar vários tipos de caras que eles aprenderam numa base de dados. Não é? Ou seja, de certa forma isto é codificação. Como é que eles codificam as caras humanas? A partir okay. Tem aqui outro muito engraçado que é... Okay. Tem aqui outro muito engraçado. Isto não sei, que era Generate Walks. Isto aqui é o mesmo. Ok, onde é que está? Estou no estado de material. Isto precisa de Java. Ok. E eles aqui têm várias demos. Se forem a deeplearning.net, tem aqui algumas demos muito engraçadas. Não, este é meu. Ok. Ora, isto eu tenho que